Today we're going to jump ahead a little bit into chapter 7 and pick up 7.7, which is L'Hopital's rule. L'Hopital's rule is going to allow us to find the derivative or the limit using derivatives of some more complex functions. So we've talked about the indeterminate form, and we've talked about one of them in particular, that's 0 over 0. L'Hopital's rule is going to allow us to find the limit of indeterminate forms other than that 0 over 0 as well. So we have other forms, 0 to the 0, 1 to infinity, infinity over infinity, or infinity times 0. Now some of these you would think, oh, that just makes sense, that would be 1 or that would be 0, but not necessarily the case. Like the 0 to the 0. That's an indeterminate form because we don't know what 0 to the 0 power is. Same with 1 to infinity. A lot of people would think, oh, that's just 1, but not necessarily going to be the case, because we know that infinity is a concept, it's not necessarily a number. So when does L'Hopital's rule apply? Well, if we're taking a limit as x goes to a of f of x over g of x, and that's an indeterminate form, what does that mean? Well, that means that as x goes to a of f of x equals 0 or infinity, and g of x, the limit, is going to be 0 or infinity. So we must state this information in order to be able to do L'Hopital's rule, which tells us that the limit of f of x over g of x as x goes to a is equal to the limit as x goes to a of the derivative of f of x divided by g of x derivative. And if we need, we can apply this more than once, which we'll see in our notes today. So let's go ahead and look at an example. We have the limit as x goes to 0 of e to the 3x minus 1 over 2x. So I'm going to go ahead and find the limit as x goes to 0 of the numerator e to the 3x minus 1. If I plug in my 0, I get e to the 0, which is 1, minus 1 gives me 0. The limit as x goes to 0 of 2x, if I plug in 0, 2 times 0 gives me 0 as well. So I have 0 divided by 0, or my numerator's limit is 0, my denominator's limit is 0. So I can put therefore, and my L'Hopital's rule is going to apply. So what does that mean? Well, what that means is that we can go ahead and find the derivative of the numerator and the derivative of the denominator and take the limit as x goes to 0 of that function. So the derivative of e to the 3x minus 1 is going to be 3e to the 3x divided by the derivative of 2x, which will be 2. Now I can go ahead and plug in my 0 again. E to the 0 is 1. 3 times 1 gives me 3 divided by 2. So my limit is 3 halves. So I know the limit of this original function is going to be 3 halves as well. So there's not going to be any reason to use your calculator to be able to find this limit. It would be definitely a non-calculator question. Limit as x goes to infinity of the natural log of x divided by 2x. So if I go ahead and find the limit of my numerator, which is going to be the natural log of x, and the limit as x goes to infinity of the denominator, which is 2x. So that limit as x goes to infinity, the natural log of a larger and larger number, is going to be larger and larger, goes to infinity. As x goes to infinity of 2x, or as x goes to infinity, 2x is going to go to infinity as well. So we can say therefore, and I'm going to go ahead and abbreviate L'Hopital's rule, L'(H), rule applies. So what we can do then is go ahead and find the derivative of the numerator and derivative of the denominator and take the limit as x goes to infinity. So derivative of natural log of x is 1 over x, derivative of 2x is 2. We can simplify that to 1 over 2x. Now as x gets larger and larger, 1 over 2x gets smaller and smaller, closer to 0. So we know this overall limit then would be 0. We can do this with more complex problems. We have the natural log, or limit as x goes to 0 of 2 to the 2x minus 1 over 2x. So with this one, we're going to go ahead and find the limit as x goes to 0 of 2 to the 2x minus 1, the limit as x goes to 0 of 2x. Again, remember, we're going to show these two very important pieces to show that the limits are either 0 or infinity. So we have 2 to the 0, which is 1, minus 1 gives us 0, Plugging into 0 here, we get 2 times 0, which is 0. So therefore, L'Hopital's rule is going to apply. And we can go ahead and find then the derivative. So we have the limit as x goes to 0, the derivative of 2 to the 2x minus 1. So we can either go off to the side and do an implicit differentiation, which I showed you, or if you remember the rule, we have 2 times 2 to the 2x times the natural log of 2, divided by derivative of 2x, which is going to be 2. Our 2's will reduce there. So if we plug in our 0, we have 2 to the 0, which is 1, times the natural log of 2, which gives us the value of the natural log of 2. So our limiting value up here is going to be the natural log of 2. We got another one here. Limit as x goes to negative infinity of x squared over e to the negative x. Here we're going to take the limit of x squared and the limit as x goes to negative infinity. Don't want to forget that, do I? Negative infinity of e to the negative x. So if I plug in negative infinity, as I square it, I'm going to end up with a positive infinity. If I take negative infinity, take the negative of that, I get infinity. So e to the infinity, that's going to get larger and larger and larger. That goes to infinity. So again, therefore, L'Hopital's rule is going to apply. So I'm going to go ahead and find the derivative. So I'm taking the limit of 2x as x goes to negative infinity divided by negative e to the negative x. Again, if I plug in my negative infinity, I'm going to get a negative infinity in the numerator. In the denominator, I'm going to get a negative infinity as well. So we should see the limit as x goes to negative infinity of 2x is going to be a negative infinity, and the limit as x goes to negative infinity of e to the negative x, the negative e to the negative x, is a negative infinity as well. Since I have an infinity over an infinity, we have another L'Hopital's rule. So I'm going to go ahead and state that it applies twice. So I have up here and also down here. So I'm going to run out of room here. So I'm going to take the limit as x goes to negative infinity of the derivative now of 2x, which is 2. Derivative of negative e to the negative x is going to be e to the negative x. Plugging in my negative infinity, now my denominator is getting larger and larger and larger. My numerator is staying the same, so I get 2 over a larger and larger number, which is going to go to 0. So my limiting value is 0. Got a few more here. I know it's a little on the lengthy side, but I want to get through quite a few of these examples. Here we have an interesting one. Limit as x goes to infinity of 1 plus 1 over x to the x. As I plug infinity in, or a larger and larger number, here we get 1 over infinity, so that's going to go to 0 as x gets larger and larger and larger. So I have 1 to the infinity, which if we remember, use the announcement there, I apologize. So that's going to go to 1 to infinity, which is going to be an indeterminate form. So what we're going to do then is have to do something with this. And with this one, I'm going to go ahead and introduce y. Y is going to equal that limit. And what I can do is I can take the natural log of both my left side and my right side. If I take the natural log of y, that's the same as taking the limit as x goes to infinity of the natural log of 1 plus 1 over x to the x. That's going to allow us to take this x and bring it to the front. So our natural log of y is going to equal the limit as x goes to infinity of x natural logs of 1 plus 1 over x. From here, I'm going to do something a little different, a little odd, but I'm going to bring this x, I'm going to bring it to the denominator. So I'm going to have this as the natural log of 1 plus 1 over x to the negative first. And it's going to make a little more sense why I do that here in a second when I go ahead and find the derivative here. I didn't put it up here, L'Hopital's rule applies, did I? So make sure we put that in there. So here now I'm going to take the derivative of the numerator, divide by the derivative of the denominator. So I'm looking at the limit as x goes to infinity of derivative of 1 plus 1 over x is going to be negative 1 over x squared over that original function, 1 plus 1 over x. And that's going to be divided by the derivative of x to the negative first, which is again is negative 1 over x squared. nice thing happens when I did that. Now my two numerators are the same, so that's going to reduce, and I'm going to look at the limit as x goes to infinity of 1 over 1 plus 1 over x. Well, what do we know about the limit as x goes to infinity of 1 plus 1 over 1 plus 1 over x? As x gets larger and larger and larger, 1 over x, that goes to 0, so I get 1 over 1. Not necessarily our answer here at this point, though, because remember this is equal to the natural log of y. So natural log of y equals 1. What I want to do, though, is to get y by itself again. In order to do that, I can think of the natural log as being base e. So if you want, you can rewrite that as log base e of y equals 1. Changing this in exponential form, we have y equal e to the first, or e. Wasn't that interesting? E, we've seen that e before. We've used that quite a bit. So that's where e comes from. The natural log, or the limit as x goes to infinity of 1 plus 1 over x to the x is equal to e. There you go. I think I did show you that in pre-calculus, but if you forgot or if you didn't think about it, there you go. Another one, we have the limit as x goes to infinity of 2x e to the negative 2x. Again, we go and plug in our infinity, so we have 2 times infinity e to the negative infinity. Wow, that doesn't quite make a whole lot of sense there, does it? But if we were to write it, we can go ahead and do that. So we have an infinity times, and as it gets larger and larger and larger, a negative, e to the, this is actually 1 over e to the 2x, isn't it? So that's going to be an infinity over infinity. So we have the limit, and I want to go ahead and rewrite that, don't I? 2x over e to 2x. Make that negative exponent positive. It's going to make our life a little easier. So if I look at the limit as x goes to infinity of 2x, that gives me infinity. The limit as x goes to infinity of e to 2x, that's also infinity. So I have an infinity over an infinity, so therefore L'Hopital's rule is going to apply. So what we can do then is go ahead and find our derivative. We have the limit as x goes to infinity. Derivative of 2x is 2. Derivative of e to the 2x is 2e to the 2x. We can reduce our 2's if we want. Ultimately, though, we have e to the infinity, if you think of it that way, or as a larger and larger number, so that gets larger and larger and larger. 2 divided by a larger and larger number is going to be 0. So the overall limit up here, we're going to run out of room there, is going to be 0 as well. All right, just a couple more examples here, and then we'll be on our way. The limit as x goes to 0, the sine of x to the x. Again, we have that x in the exponent. How are we going to get rid of that? Well, we can take the natural log of both sides. The natural log of y equals the limit of the natural log of the sine of x over x. Again, so if we plug in our 0, I guess we should make sure L'Hopital rule applies. If I plug in 0, sine of 0 is 0, and then to the 0, so we end up with 0 to the 0. So therefore, L'Hopital rule will apply. So we're looking at the limit as x goes to 0 of the natural log of the sine of x to the x. We can bring that x to the front of the natural log of the sine of x. We can then go ahead and bring, again, this x to the bottom. So we have the limit as x goes to 0 of the natural log of the sine of x over x to the negative first. That's going to allow us to go ahead then and find the derivative of this fairly easily. We have the limit as x goes to 0. Natural log of the sine of x gives us the cosine of x over the sine of x divided by negative 1 over x squared. I'm going to go ahead and manipulate this a little bit. We have the cosine of x over the sine of x, which is cotangent of x, and that's over negative 1 over x squared, so we can write our negative x squared in the numerator as well, multiplied by the reciprocal. And then what I'm going to do is, I know cotangent is 1 over tangent, so I'm going to write this as negative x squared over the tangent of x. And that's going to make my life a little easier, I think, because then I can go ahead and I'm looking at the limit as x goes to 0, or of x squared, which is 0, tangent of x, that gives me 0 as well. So again, I can write that out. The limit as x goes to 0 of negative x squared equals 0. The limit of tangent of x as x goes to 0 is 0. So therefore another L'Hopital's rule is going to apply. So I can go ahead and find the derivative then of the numerator and denominator. So I'm taking the limit as x goes to 0. Derivative of negative x squared is negative 2x. Derivative of tangent of x is going to be secant squared of x. Now, as x goes to 0, negative 2x goes to 0. Secant squared of x is going to go to 1. Remember, secant is 1 over cosine. So the cosine of 0 is 1, so we have 1 over 1, which gives us 1. Well, 0 divided by 1, that's going to be 0, isn't it? So now, we have the natural log of y is going to equal 0. Again, natural log of y equals 0, we can change that to exponential form. So e to the 0 equals y, e to the 0 is 1, so we get 1 equal to y. So the limiting value there is going to be 1 again. Last but not least, we're going to go ahead and do this definition of derivative. We've worked with this quite a bit. If we plug in 3, we end up with 0 over 0. So we have the limit as h goes to 3 of the square root of x minus 1 minus the square root of 2 equals 0. The limit as h goes to 3 of x minus 3 equals 0. So L'Hopital's rule will apply. When we did this before, I told you to go ahead and conjugate it. If we didn't conjugate it, we could have found the original function and then found the derivative at that point. What we can do with this, though, is now with the definition of derivative, we can use L'Hopital's rule to make our life a little easier. So what can we do? Well, we'll find the derivative of this. We're taking the limit as h goes to 3. The derivative here is going to be 1/2 of x minus 1 to the negative 1/2 times 1 with our chain rule. The limit of our denominator, or the derivative of our denominator, is going to be 1. Plugging in my 3 now, we're going to get 1/2 of 3 minus 1 to the negative 1/2. That's going to go to 1/2 of 2 to the negative 1/2. And then from here we can clean it up as much as we want. Maybe 1 over 2, and then 2 to the 1/2, or 2 square root of 2, depending on how you want to see that. So that gives you an idea of where L'Hopital's rule is going to apply and how to apply it in several different cases. If you have any questions, please reach out and we'll get those taken care of. Good luck and have fun finding the limits. Happy limiting!